All right, we're gonna get started on chapter 4. Section 4.1 is just some historical perspective concerning the theory of congruences. The language of congruences, or the concept of congruence, was actually invented by Gauss. It appeared in a book that he published, or first published actually in 1801, and in Latin. Gauss at the time was 24 years old, and the name of the book is, I cannot pronounce this, was Confluences Arithmetic. Actually, this treatise of Gauss laid the foundation of modern number theory. In other words, number theory is known since the Apollonian and even before that, and it was kind of scattered, results, but Gauss kind of put it in a form that actually what nowadays we call actually more or less the modern number theory. What the congruences, or the concept, or the theory of congruency allow us is to think or work with the divisibility relations as working with equalities, which means things we set them actually as equations, or at regular equality regular equations. All right, so this is it as far as section 4.1. I'm going to leave the rest of this section for you to read. There are some nice kind of ideas in there concerning the life of Gauss and some of his accomplishments. All right, so now we move on to the section 4.2, and I have listed the main objectives of this section 4.2. So we're going to get started, of course, by defining what this congruence relation, we're going to find it is actually a binary relation defined on the set of integers. Then we're going to move on to proving some basic properties of congruences, what kind of properties they satisfy. And in particular, we're going to describe, the behavior of this relationship with respect to the arithmetic operations, which is addition, multiplication, division, of course, addition, subtraction. And then we're going to end up with looking some illustrative examples of the use of congruences that we will be continue working on the coming sections. That means the different applications of congruences. All right, so let's get started with the definition. All right, so here is the first definition. So let's let M be a positive integer for A, B, and Z. We say A is congruent to B modulo M if M is divisible by the difference between A and B. All right? So in other words, we're given two integers. We say that these two integers are related, basically, what we call is congruent to mod M if M divides the difference between A and B. We're going to use the actually the notation or the symbol used by Gauss to express this relationship, all right, between A and B. So if A is congruent to B modulo M, we express this by this symbol, or in symbols by as a, like equality sign, we put congruence, and this will go congruence B, and then we put mod M. Okay? So we put mod M between parentheses. So in other words, so we can shorten this definition by saying that given M a positive integer, A, B in Z, we say or we define, actually maybe, but we say, okay, A congruent to B mod M, if and only if M divides A minus. Of course, on the other hand, if M does not divide, because an integer either divides another integer or it doesn't divide. If it doesn't divide, we say that A and B are not congruent mod M. Okay? So if M does not divide A minus B, we say A is not congruent mod. And in notation, we express this by saying that A does not satisfy this relation with B. Mod. All right, let's look at some examples. Okay. So, for example, we have the 3 is congruent with 24 mod 7, because the difference, since 7 divides the difference between these, which is negative 21. We also have another example. Negative 31 is congruent to, for example, 11 mod 7. So the number we take to be congruent, it could be positive, negative, 0, and so on. So in this case, since negative 31 minus 11, which is negative 42, of course, and we have 7 divides that. So 7 divides this difference, and this is it. On the other hand, when you look at the 25 and 12, no, this does not, it's not congruent, mod 7, because we have 7 does not divide 25 minus 12, which is 30. All right? So either we have an integer either congruent to another integer mod 7 or it is not. And even we could look at 49 is congruent to 0 mod 7. Right, because of course 7 divides 49. In fact, we come with the first property of congruences, that is is this. So we have A is congruent to 0 mod M. All right. Let me put it actually a quantifier in it for every A in Z. A congruent to 0 mod M if and only if M divides M. Let's look at the quick proof for this. So let's assume that the congruence relation is satisfied. A is congruent to Z, to 0 mod M. And this is equivalent to saying that M divides M. And that's it. The other way, if M divides A, this implies M divides A minus 0, and this implies that actually A is congruent to 0 mod M. Actually, this is, what Gauss has in mind is to convert, okay, a divisibility relation to some sort of equality, because could think of this in some sense an equal, okay? What we call a modular equality or equality mod a positive number. All right. Next, let's look at expressing the congruence relation between two numbers as an equation, basically. In other words, a generalization of this. This one is A and 0. So we have the following theorem. Which says the following, right? If A and B are integers, and M a positive integer, always the number that we take using for a mod, always positive. Even if we don't state there, from here on, always M, we can assume it is actually a positive integer. So if this is the case, then we have A is congruent to B mod M if and only if A is equal to, so this is an equation, B plus Km for some integer K, or some integer K. All right, let's go ahead and prove this. This is very, very straightforward, simple, all right? The idea of it is, again, to think about congruences in different ways, okay? So let's assume, going this way, again, let's assume that A is congruent to B mod M. By definition of this congruence relation means M divides A minus B. And by definition of divisibility means this implies there exists a K in C such that A minus B equal MK. And this in itself, if we solve for A, we get A is equal MK plus K. Conversely, let's assume that A is equal B plus or MK plus B, or B plus MK, for some K. And again, this implies as an equation A minus B is equal MK. And also we can express this by saying that M divides A minus B, because A minus B is a multiple of M. Okay, very straightforward. All right. Let's look at an example, all right, of this. So any congruence, that's what the example shows, that any congruence I can change it into an equation. So if I look at this equation, 19 is congruent to negative 2 mod 7. All right. This is equivalent to saying that I can write 19 as negative 2 plus some k times 7. And of course, in this case, the k that works in here is a 3. So this one is need to be 3. So in other words, this is what we're saying is negative 2 plus 3 times 7, which actually is a correct statement. All right, now we're going to start proving some basic properties concerning this relation. The first theorem, we're going to see that this relation is actually the congruent relation, mod M is an equivalence relation. Okay, so this is a theorem 4.1, actually part of theorem 4. I want to separate them because this actually convey or say certain properties of the congruence. This is from A to C. And this is what it reads, that again, that M be a positive integer and A, B, C are any integers, then first thing is A is congruent to A mod M, and this is for every A in Z. This property we describe it by the relation congruent is reflexive. Okay, so this it says that is congruent mod M. Another strange way of writing it, this relation is reflexive. Or we say it's a reflexive relation. Second, say that if it happens that A is congruent to B mod M, then B is congruent to A mod M. This relation says that the congruence relation is symmetric. So the same relation is symmetric. And the third one, it says that if A is congruent to B mod M and B is congruent to C mod M, then A is congruent to C mod M. So express that, so AB, BC, we can go all the way from A to C. We call this that the congruence relation is transitive. Of course, you are familiar with many types of relations that they satisfy these three properties, the reflexive, symmetric, and the transitive. Let me mention a couple of these. The equality of numbers, real numbers, integers, and so on. Of course, they satisfy these and many other types of properties. Another one is two lines in a Euclidean plane being parallel to each other. So as we know that every line, we could think of it as parallel to itself. If you have L is parallel to another line L prime, then L prime is parallel to L. And the same thing if you have three lines, one is parallel to another one, and the second one parallel to the third, then the first is parallel to the third. All right? So these are all satisfy these properties. Any relation that satisfies these similar properties to these, we call it, that this relation mod M, or the relation on the set of integer, which is congruent mod M, is an equivalence relation. It's an equivalence relation. And knowing this, there are a lot of results, a lot of theorems concerning equivalence relation. When you have an equivalence relation, we're going to see that this equivalence relation partition means separate, divide the set of integers into subsets of integers, and those subsets of integers, they don't have any number in common, means they are disjoint. And when you take their union, it gives you all the set of integers. And one other thing, the integers in each of these subsets are congruent to each other, and any number on one of these subsets is not congruent to a number on another subset. Okay? These subsets we're going to study more, and these are called congruent classes. Okay? Congruence classes or congruent classes. All right. The proof of this is very, very simple. Let's go ahead and present it. All right, here's the proof. For the first one, we want to show that A is congruent to A mod M. Well, this is equivalent to showing that M divides A minus A, all right? But this is equal to 0, and yes, this is true, okay? Since 0 is equal M multiplied by 6. So, yes, 0 is a multiple of M, basically. Second one, if A is congruent to B mod M, this implies that M divides A minus B, and this implies that A minus B is equal to K M for some K in Z. Now I would like to look at B minus F. Okay, so if I multiply this equation by -1, I get B minus A equal minus K multiplied by M. So once again, B minus A is a multiple of M, and by definition, this implies that M divides B minus M. And again, by the definition of congruence, this means that B is congruent to A mod M. So in other words, looking at the difference, which number comes first, congruence, either A is congruent to B, implies B congruent to A. So these are what we call the symmetric, these two where the A and the B are related. All right, let's look at part 3. A congruent to B mod M implies, and again, I could write this as an equation, remember from previous theorem. So I could write this as A equal B plus K1M. And the other relation says that B is congruent to C mod M. And I can express that by saying B is equal C plus K2M. Now the K1 and the K2 in here are in Z. For some, K1, K2 in Z. Now I can substitute for the B from the second equation in the first. So this implies that A is equal to C plus K2M plus K1M. And rearranging the terms of this equation as C plus K2 plus K1 parentheses M, and this is exactly what it means for A and C to be congruent. So this implies that A is congruent to C mod M. Alright, so this is it. So these are all the properties. And again, I say that means that the relation congruent mod M is an equivalence relation. And if you are familiar with, again, what this implies about the behavior of this congruence relation, then you can say that. All right. Let me move on into another theorem. Before we actually prove more properties of just this congruence relation, so this is theorem 4.1. We're going to see that this theorem provides another definition, another way actually of looking at two numbers being congruent to each other. Again, let M be a positive integer, A, B are in Z. Then A is congruent to B mod M if and only if A and B leave the same remainder when divided by M. Right? So any theorem that is an F and only F, we can use this as a definition. So based on this, we can define that two numbers are congruent if actually when we divide A and B they produce the same remainder. So the integers are, in other words, congruent to each other if they have the same remainder when we divide each one of them by m. All right, let's go with the proof in here. So let's assume that A actually divide congruent to. So we're going to assume A is congruent to B mod. I would like to show that they leave the same remainder. All right. Well, we can, go about this in different ways. Okay. First of all, we can use the previous theorem before the previous theorem that this congruent means A is equal to B plus mk for some k in Z. All right. Also, we can apply the division algorithm to B and M, and this would imply that I can write B as the QM plus R for unique actually, the Q and R, Q integers Q and R in Z, where the R is bigger than or equal to 0, is strictly less than M. Okay? Now, let's substitute for this P in the first equation. Okay, so this implies that now A is equal, we write this one more time, mk, and I've been substituting for what P is equal to, so this is equal to Q M plus R plus mk. Now remember the R, the Q, and the K are unique, because when we're saying the K here, there is only one K that actually makes this equality. And again, arranging these, I could write this one as the Q plus K M plus R. And remember the R is between actually this, all right, M. Now, so this is saying that we can express A is in a unique way as a multiple of M plus R, then by the uniqueness, by the division algorithm and the uniqueness, and uniqueness of R, that's the remainder. This implies that A leaves a remainder, of R when divided by M. Similarly, from what I have also in expressing, the B, all right, in a unique way, also B leaves the same remainder, right? So moreover, over B leaves the same remainder. Namely, namely R when divided by let me say namely actually. Namely R when divided by F. Alright, so this takes care of one direction of this theorem. Let's go the other way around. Let's assume that when we divide A and B by M, we get the same remainder. And this remainder, of course, we can obtain via the division algorithm. Okay, so I'm going to go this way. So let's assume that A and B leave the same remainder. Let's say R. R when divided by. Okay, this implies that I can express as A as a Q1M plus R and B Q2M plus R, where the Q1, the Q2, and R are all integers, and the R is between 0 and M. Now I need to show that A is congruent to B, all right? Well, when we solve each one of these for R, we obtain, this one implies that R is equal A minus a Q1M, and this gives us R is equal B minus Q2M. So I can put these equal to each other. And I can rearrange this as A minus B is equal to Q1M minus a Q2M, which I can write as a multiple of M. And this is exactly implies that M divides A minus B. Because A minus B is a multiple of M, and this in itself implies A is congruent to B mod. All right. Now you can see the simplicity actually of working with this congruence and divisibilities using this congruence relation. All right. I want to introduce some actual vocabulary. Now, sometimes we use congruence in a slightly different way. And this is usually used more in computer science, okay? Now another common notation used especially in computer science, where we write something like this: A mod M, and we put equal R. This is what the meaning of this. This means we are reducing, sometimes we say, A mod M to, let me see what's the word I want to use in here. Reducing M by replacing basically A by the remainder R that A leaves when divided by M. All right, let's look at an example just to kind of illustrate this idea. For example, if you take a 17 mod 5, okay, we can say this is actually is equal to 2. So what we are replacing the 17. When you divide this is by 5, you come up with a 3, all right, and the remainder is actually equal to 2, all right, 15 and a 17. So sometimes we use actually this language. Another one is like minus 8 mod, let me see here what's the number I have, 7 is equal to, actually is equal to 6. All right, so if you divide negative 8 by 7, remember that this time we're going to have the remainder to be positive, so and that's going to be equal to 6. All right, so minus 8 over 7, it gives you negative 1. All right, and the remainder is actually 6 over 7 to get what is this actually for this to work, right? Let's see in here. Minus 7 plus 6. Okay, so minus 8 over 7. All right, yeah, if I minus 8 over 7. How are we going to write this one? So, in other words, we write negative 8 is equal minus 1 times 7 plus 6. Well, that's not an incorrect. This is an incorrect statement. So, let's see here. Probably we need minus 1/7. All right. Yeah, actually, I need the 2 here, right? We need a negative 2, that's negative 14, plus 6 is equal to negative 8. So this is all right, so this is actually the least positive or non-negative, remainder when we divide negative 8 by 7. So we can try to conclude from this discussion that this theorem in here, just to translate this in use of the notation. So A is congruent to B mod M if and only if all right, A mod M is equal to B, actually is equal to B mod M. All right. All right, and you know, this is kind of a little bit strange notation, but remember that we are using for this the remainder that, all right, A leaves when divided by M, and we say that if two numbers are congruent to each other, the same remainder. And we are saying these are equal as, you know, using basically this notation. All right, and this actually allow us to think of this relation mod M as a function from the set of all integers to the possible remainders that we get when we divide any integers by M. All right? All right, this notation which is the notation is A mod M is equal R, okay, allow us to think of the relation M mod M on the set of integers Z as a function denoted by mod, kind of a little bit weird notation, but we will replace this by something little nicer. Okay, so this is the function goes from Z to the set of integers 0, 1, 2, up to M minus 1. And actually this function also it is surjective. Okay, so this is a surjective function, or another name for surjective is onto function. So it assigns with every integer, you know, the remainder that integers, you know, gets or have when we divide it by M. Another notation we use for this is this bar, okay, from Z to 0, 1, 2, up to M minus 1. Those of you who have taken some courses in abstract algebra and so on, probably they use this one or they use the bracket. For example, if we take M is equal to 5, then this function, all right, takes Z into 0, 1, 2, 3, 4. Up to 4. And when you look at, for example, 8 bar, all right, you assign to this, you know, they're actually 3. All right, this is the same as the 3. And we're going to see also, when you look at the 3 bar, is going to be the same as 8 bar, and so on. Because they all leave the same remainder, so they are congruent to each other mod 5. All right, now we need to move into these ideas about you know, equivalence relations and what do they do. Well, here's another discussion. First, we start with the discussion. Yeah, I want to do this one in a little bit general setting. So if we have an equivalence relation on a set, let me put it X, then this equivalence relation, let me put it, this is as a fact actually, okay? Then the equivalence relation what we use over here is a technical term. We say partition X into subsets with the following properties. Of course, these subsets of X, okay, with the following properties. First, the union of these subsets of all the subsets is X. All right. Two, the subsets are disjoint. Any two of the subsets are disjoint, not just all of them. Any pair of subsets are disjoint. This means if you take the intersection, let's say we have an A and a B, their intersection is empty. So in other words, we could think of if we have a equivalence relation in a set, so let's say this is a set represented by a Venn diagram, then the set partition X into subsets which have no points in common, disjoint. These does not have to do anything with the other ones, all right? And it cut the whole X into these subsets that give us all of set when we take their union. So we're going to take the union A1, A2, say in this example A3, A4, A5. One other property they satisfy, it is, or two properties rather, that all the elements in A1 are congruent, okay? They are related by this equivalence relation. The elements in each subset are related to each other by the relation. And the last property they satisfy, number 4, is elements from two different subsets in two different subsets are not related. Of course, by the relation. All right. So this is true for any equivalence relation. Now we want to look at, what does this translate to in our congruent mod M relation. All right. So I want to define what it means to say that two, again, integers are congruent to each other mod M using this language, basically. Here's a definition that we'll need. Right, if A is congruent to B mod M, then we say that B is a residue you see, say residue of A mod M. So this is kind of, again, another way of expressing, that when we have a relationship between A and B, we use this. And this is an appropriate name because the word residue means something left after doing something. And what it's this operation that we do is when we divide, A by M, all right, it actually could leave a residue of B, or of course another remainder that would be also leave when we divide it by M. Moreover, since this relation is symmetric, we can say similarly, we say that A is a residue of B mod F. All right, now let's define the following. So we're going to define this subset. Define the subset that we denote by E sub A to consist of all the integers x in Z such that x is a residue of A mod F. So in other words, if I want to write this in the using the notation of congruence, so this consists of x in Z such that x is a residue of A mod N means x is congruent to A mod M. All right? And if we simplify this a little bit more, we could say this is those integers x and z such that, and I could replace this congruence relation by saying that M divides x minus A, and we could write this divisibility relation as x in z such that x minus A is equal mk for some k in z. We're going to arrive at a nice description of this set. Okay, these are, remember, this is actually a subset of integers. So this one is a subset of z from the way we have defined x is in z. All right? And remember, the relation is defined on the set of integers, and what we're going to come up with those subsets that I mentioned in this in connection with equivalence relations. Okay. All right. Let's do it one more steps maybe. So let's go in here. So this E sub A, it's going to consist of x and z, such that we write the last statement in here, which is x minus A is equal mk for some k in z. Now, this some k's in z, it gives us one of the x's. And if I still write this, such that x equal A plus mk again for some k in z. Now, if I want all of them, all the x's that can be expressed this way, I can write this without actually mentioning the x anymore. Because the x appears in two places in here and there. And I could say, well, this set is the same as A plus mk, such that k belongs to z. So if I consider all possible k's, each one of these k's is going to give me a different x, and this is what this E sub A is. Now, the elements of this set, we call this is a residue class. All right, this subset E sub A is called the residue class mod M of, or determined by, maybe a better word, determined by A, or of A, if you wish. Yeah, we would like to look at the different, okay, properties of this class together with, you know, its properties with other ones. All right, here are the first property is this. So properties of E sub A. One, A belongs to E sub A. Okay? Two, if A, B are integers, then the E sub A will be the same as E sub B if and only if A is congruent to be mod M. And three, E sub A intersection E sub B is empty if and only if A is not congruent to be mod M. Number four, if we take the union of all these subsets as A ranges over Z, this is of course will equal to all of Z. In fact, we're going to see a lot of these subsets, they're going to be kind of, they're not all, destroyed or different. In fact, from 2 and 3, what we are basically saying that either two residue classes are equal to each other for two different integers, all right? And this happens if A is congruent to B, and if A is not congruent to B, then they are disjoint. Okay? So these are very, very much related to each other. In fact, this is the contrapositive of each other, basically. All right, in some sense. All right? So these are equal, or they are totally strangers. I mean, they don't have anything in common. All right, let's go ahead and prove some of these. Okay, so let's just start with the first one. Well, remember that first of all, let's write what this E sub A means. Is the proof. E sub A, by definition, this is equal A plus mk, such that k ranges over all the integers. So definitely A belongs to E sub A, since A is equal A plus m times 0. So the k equals 0 gives me the A. All right, let's look at the second one. The second one, it's an if and only if. So let's assume that E sub A is equal E sub B. All right? And I need to show that A is congruent to be mod M. Well, from part A, I know that A belongs to E sub A, and B belongs to E sub B. And since these are equal, then I can say A belongs to E sub B, or the other way around. Well, what does this mean? This means that A is equal to, okay, because in E sub B, it's going to be B plus M K for some K in Z. And this is exactly what it means, that A minus B is a multiple of M, and this means that A is congruent to B. And this argument is almost basically reversible. That is, if A is congruent to B mod M, then we have this, then we can express A in this form, and then we can have A is in EB. And we can do actually, this is for A, and that means if we want to show this the other way around, let me actually do that. Means those in more general setting. So let's assume that A is congruent to B. So let's go this way. Assume that A is congruent to B mod M. Now I wanted to show that E sub A is equal to E sub B. So all we have to do is to show each one of these is actually a subset from the other. So we want to show that E sub A is contained in E sub B. So let's take an X in E sub A. This implies that X is equal A plus Km for some K in Z. All right? And now we need to somehow show that X is also in EB. Now we have, since A is congruent to B mod M, this implies that A itself is equal B plus L sub M for some L in Z. Now we do substitute by what A is equal to in terms of B. In the previous equation, we get this equal B plus Lm plus Km. And once again, we see this is B L plus Km. And this means that actually X is in E sub B. So this shows this way, and by symmetry of the argument, we have the other way around. So we also can show or say yes, this is true by symmetry, and then we are done. The last part, or the part after that, if actually, as I said, it's basically the contrapositive. So if A is not congruent to B, let's go ahead and sketch the proof again here. This is number 3. Let's assume that A is not congruent to B mod M. And need to show this to show E sub A intersection E sub B is empty. Let's assume by contradiction assume they have something in common. That E sub A intersection this does not equal the empty set. This implies there exists an X that belongs to both E sub A and X belongs to E sub B. And if we write, what does this mean? Means x is equal a plus mk, and this means x equal b plus ml for some k, l, and z. Which means that these are equal to each other. And which makes a minus b is ml minus mk, which is a multiple of m, and which make them actually congruent, which is of course a contradiction, because we are assuming they are not congruent. Converse it's pretty much the same, all right? If these are, they have an empty intersection, assume that A is congruent to B, and actually reverse basically this argument. All right? And the very, very last part is actually the union of all of these A sub A, as A ranges over all the integers is going to be also all the integers, because at least each one of these contains A. So you take the union, really we're taking the union over all of Z, and this is would be the case. All right. Now, in particular, all right, since we know that two congruence classes are equal to each other if and only if A is congruent to B, then we have one special residue clause so we have that so we can say this. So E sub A, all right, this consists of integers that leave the same remainder when divided by m. All right, so with this, then we have, since the set of remainders of dividing any integer by m are these: either 0, 1, 2, up to m minus 1, then there are m, what I call these are m residue, m different or distinct, m distinct, because of that. Remember, the intersection is empty if they they are not congruent. So distinct residue or distinct. Let me see here. Yeah, called residue classes mod m. namely E sub 0. Each one of these you call it residue class. I don't know if I did use this language or not. So these are called the E's. We call them residue classes. And then we have E1 and so on up to E m minus. Now let's look what these different residue classes consist of. Okay, so let's look at an example. Actually, we could describe them in here in general. So E sub 0, this is all the integers that leave 0 when divided by m, right? So this is going to be actually mk, such that k is in z. Then E1 are the integers that leave a remainder of 1 when divided by m. And this is by the division algorithm. This is going to be 1 plus mk, such that k is in z. And so on. So the last one is E sub m minus 1 is the m minus 1 plus mk. Such that the case, of course, in here ranges over all the integers. So in particular, if I look at the case where m is equal to 3, then we have 3 classes, the 3 E sub 0, and these are going to be the multiples of the 3, so we write 3k, that's k in z. And I can write this one actually as a 3z, something like this. Multiples of the integers by 3. Each integer is multiplied by 3. And E1, it is 1 plus 3k, same thing, k is in z. And we actually could name them, of course, okay? And this one is going to be 1 plus 3z, so we have use of notation, we could use this. And of course, E2 is 2 plus 3k. Or in other words, the integer that can be written in the form of 2 plus 3k. We actually been using this language, all right, before. Now we see, another way of looking at it is using congruences, 2 plus 3. All right. Now we refer to the integers that produces all these distinct residue classes. We call this is the least, non-negative, all right, residues mod m. One more definition. It's annoying, just some of these definitions, because they're very much related to each other. But hopefully you will kind of distinguish between the little differences between them, okay? So, one last. Definition in here. The set of, here's the definition. The set of integers 0, 1, up to m minus 1 is called the least. It's called the least non-negative residues mod. So least negative, they're all non-negative residues mod. Now, for these E's, go back to the example of for m equal to 3. So we have the least non-negative residues for this is, of course, is 0, 1, 2. Okay? And the residue classes they produce is E sub 0, which is multiples over 3, E sub 1, multiples over 3 plus 1, or the number that leave 1 when divided by 3, and then we have E2, those integers that leave remainder of 2 when divided by 3. All right? Now, we know that the union of these, of course, is going to give us all of the integers. All right? So the E sub 0 is going to be a subset, right? And sometimes we denote this, all right, by putting a bar over the 0. So the 0 bar means it's the subset E sub 0. And we write this one as 1 bar, and we write this as 2 bar. All right, some other authors, they use brackets around this, and they put, sub 3, okay? And they denote this is by 1 sub 3, and this is 2 sub 3. All right? There are other ways we could represent the equivalency classes. For example, if you look at E sub 3 itself, this means all the integers, the meaning of this is equal to 3 plus 3k, such that k is in Z. And this is the same as actually E sub 0. All right? So it's not hard to see that E sub 0 is the same as E sub 3, is the same as E sub 6, is the same as E negative 3, and so on. So there are infinitely many of those, and this is true for the other ones. For example, E1 is the same as E4, which means just keep adding or subtracting a 3. All right? Now, if I take instead of the 0, 1, 2 as what we call which we call the least non-negative residues mod M, we could take some other ones. And I want to define this concept that if I replace each one of these 3 by something equivalent to, we call this is a complete residue system. All right, mod M. All right, let's put the precise definition down. Here is the definition. A set of M, okay, integers, positive, negative, 0, okay, A1, A2, up to AM is I can write it in here, which consists of exactly one integer from each of the residue classes mod M is called a complete residue system mod M. Might look kind of a little bit strange, but we're gonna look at let's look at an example of this. And again, let's consider M equal 3. All right. Now remember that the residue classes for M3, the one which we use the least, all right, non-negative residues mod 3, which are 0, 1, 2. If you take any number that is congruent to 0 mod 3 as your A1, of course we could put these in any order, but let's put them in one order in here. For example, I could take instead of 0, 9, because 0 and 9 leave the same, divide the same remainder. Then 1, I can replace this is by 1 plus any multiple of a 3, or you could subtract, and let me make this one is actually 16. And for 2, you can take 2 itself, or you can take actually 2 plus 6 is 8. All right, this is an example of a complete residue system, because each one of these, it consists of 3 elements, as you see, and each one of them belongs to, different residue classes, okay, running from each of the different residue classes. There are infinite many of these complete residue systems, okay, as far as the list of integers that satisfy the properties of this definition. All right. Let me state a couple of facts, all right, concerning these complete residue systems. Okay, I don't want to go through proofs of these, they are not proved in the book, so I'll just make them as facts. Well, here's the fact. 1, a set or a subset S of Z is a complete residue system mod M if and only if it satisfies these 2 conditions. 1, S has M elements. 2, no 2 integers, 2 elements in S are congruent mod M. So it's very natural, okay? Another fact is this: how to, if we are given a complete residue system, how we come up with, other complete residue systems from it, how we generate, different complete residue systems. And this theorem, it just tells us that if R1, R2, up to Rn is a complete residue system, mod M And for any A in Z such that greatest common divisor of AM is 1, and for every B in Z, this set, which is A1 R1 plus B, A2, A R1 and then A R2 plus B and so on up to AR. Let me see. It's supposed to be this is M minus 1. Let me say it, but this is M minus 1. You have to have M. There are M of those. All right, M. This one is a complete residue system. Right? So this is a systematic way that you actually can find complete residue systems. All right, I think I'm going to stop right here. There are a few other things left in this section, so I think I will present this on a the next lecture. All right, so let me stop right here.